So today we have Dr. Ibrahim Kucukdemiral within our midst, and the topic for discussion is when data becomes therapy, data-driven predictive control for the treatment of cancer. I will hand over to Engineer Paul to give a brief introduction of our speaker, from where he will then take it over. But however, just few tips, please. If we kindly advise that everybody mutes your devices unless you want to ask a question and you signal to ask a question. As part of health and safety, this is going to be a 1-hour webinar. You could get some water, on the side to help you while you're seated. So Engineer Paul, are you there? Can you take over and introduce our guest, and then our guest will share screen and present to us? Thank you.
Yeah, thank you, Mr. Chairman and fellow engineers. This is the brief biography of Dr. Ibrahim Kucukdemiral. He is a reader in the Department of Applied Science at the School of Computing, Engineering and Built Environment at Glasgow Caledonian University. He serves as a chair of the IEEE Control System chapter of the UK and Ireland section. He is a member of the IEEE Region 8 Conference Coordination Committee. Additionally, he is the chair of the Industrial Advisory Board for the Electrical and Mechanical Engineering Department, and he co-leads the robotics for the Common Good Research Group. Dr. Ibrahim completed his BSc, MSc, and PhD degrees in electrical engineering at the Yildiz Technical University, YTU, in 1997, 1999, and 2002, respectively. His early academic career spanned from a research and teaching assistant position at YTU in 1998 to 2004, to roles as assistant professor 2004 to 2010, associate professor 2010 to 2015, and full professor 2015 to 2017 at the same university. He was instrumental in establishing the Control and Automation Engineering Department in the School of Electrical and Electronics Engineering at YTU in 2008. Dr. Ibrahim's research, let me take that again. Dr. Ibrahim's research interests cover a range of control engineering topics, including robust, optimal, and adaptive control systems, model predictive control, computational and data-driven control, and their applications in mechatronics, renewable energy systems, autonomous vehicles, and robotics. As a fellow of the Higher Education Academy in the UK, a senior member of the IEEE, and a member of the IFAC, Dr. Ibrahim has contributed extensively to academia through teaching, supervision, and module leadership. He has taught approximately over 24 of different modules at institutions such as YTU and the Turkish Air Force Academy and the University of Sharjah in the UAE. Dr. Ibrahim is an editor of Results in Engineering. It's a Q1 journal and serves on the editorial board of Ocean Engineering, that is another Q1 journal, and the Turkish Journal of Electrical engineering and computer sciences. He has supervised 5 PhD students to completion so far and continues to provide consultation and review services for various industrial and academic projects globally. Dr. Ibrahim serves in the EPSRC Peer Review College. He is also serving as an external examiner for some universities in England. He is also a member of the thematic leadership group for robotics and autonomous systems, part of a strategic partnership among Scotland's universities. That is the brief biography of Dr. Ibrahim Kucukdemiral. May I use this moment to make welcome our guest speaker, Dr. Ibrahim, to please come on board.
Thank you very much.
Thank you, sir.
Paul, thank you very much, Chair, for inviting me to this fantastic meeting and to be a part of this group for this session. I would like to share my screen with you right now so that we can continue with the presentation. I hope this would work. Would you able to see it clearly right now?
Yes, sir.
Yes,
Very good. Thank you very much. Then let's get started. Okay, good afternoon, everyone. Thank you for joining today's session. This seminar hosted by Nigerian Society of Engineers Glasgow Branch. My name is Ibrahim Kucukdemiral and I am from the Department of Applied Science at School of Engineering and Built Environment of Glasgow Caledonian University. Today, I'm very excited to share with you an innovative approach to cancer treatment, and it is titled as When Data Becomes Therapy, Data-Enabled Predictive Control for Cancer Treatments. Although the acronym is DeepC is coming from the Data-Enabled Predictive Control, please note that this is nothing to do with deep learning. This work is just an application of the very recent results of the Williams fundamental lemma on the application to model predictive control. This work is in collaboration with IEEE Control System Society and UK and Ireland section, and also Glasgow Caledonian University IEEE student group. I hope to show you how data-driven control becomes a good application area for the system biology and biological sciences, particularly for challenging cases like very aggressive cancers. Let me continue with the next slide. Let me start with some unpleasant motivation. Since this is about cancer, before we dive into technical details, let's start with some bad motivation. Cancer is a devastating disease that affects millions of people worldwide. Despite significant advances in this area, medical science, it remains a formidable challenge. Traditional treatments like chemotherapy and radiation, while effective to some degree, often come with severe side effects and lack the precision needed to target tumors optimally. This creates, I guess, an urgent need for new approach, one that can enhance treatment efficiency, reduce toxicity, and improve patient outcomes. And that's where maybe data-driven control methods, like the one we will discuss today, come into play. Why cancer remains a tough nut to crack? Let's look at the facts. Cancer is the second leading cause of death globally, claiming around 10 million lives annually, just behind the cardiovascular diseases at 18 million deaths per year. Traditional therapies, although they are very effective, are often toxic. That's the main problem, and imprecise. And we are always trying to use one-size-fits-all technique. Moreover, the economic burden is immense. By 2050, as you will see from the graphics on the right-hand side of your screen, just over here maybe, let me open the cursor. On the right-hand side, by 2050, annual cost of the cancer in the UK is projected to exceed 14 billion per year, almost double the NHS current cancer budget. These numbers, just over there you see, highlights the critical need for innovative, first of all, cost-effective and precise treatment strategies to address this growing crisis. Let's talk about some metrics. These are the statistics taken from literature. Some of them are old, some of them are very new, but these are the ones taken from robust sources. In 2022, there were 20 million new cancer cases globally, a number expected to rise to 28 million in the upcoming years until 2040, about a 55% increase from 2020. That same year, cancer caused 9.7 million deaths, showing that the current therapies fail many patients. And lung cancer, which is our focus today, accounts for 18% of all cancer deaths, while 124 new drugs were approved between 2003 and 2021. Many lack broad efficiency and affordability. They are very expensive. They cannot be used in every country. Most of the social government bodies are not providing these medicines. And as you will see, they are not reachable by everyone. And in the UK, 45.5% of cases are diagnosed at stage 3 or 4, which is the last stages, and these will limit the treatment success. These figures underscore the urgent need for breakthroughs, especially for the lung cancer, which is one of the deadly ones. Okay, now let's come to the point. Control theory meets biology. Let's explore how control theory can intersect with biology to improve cancer treatment. In traditional cancer therapy, we administer a drug or therapeutic agent and hope for a positive health outcome from the patient. Although the loop over here looks like a feedback closed loop system, this is typically an open loop process because there is no real-time feedback. And there is also human in the loop. And when we have a human in the loop, as you will see, and as you probably know, we don't call it an automatic control system. And this can lead to using human in the loop like this one and not using the real-time feedback lead to suboptimal dosing, where patients might receive either too much drug or causing toxicity or very little, leaving the tumor untreated. And here, at this point, I guess, control theory offers a way to close that loop and make the treatments more precise. Okay, now, since we are dealing with automatic control systems, we can take out the human from the loop and replace it with a computer. To address this, we can introduce computed cancer treatment. This approach uses computational models. Model is needed in order to run the controller, and control algorithms to dynamically adjust therapy based on real-time patient data. This data can be taken from online or real-time blood tests or some imaging techniques such as CTs, PETs, and so on and so forth, or MRIs. This could improve the efficiency, putting the computer over there, by ensuring the right dose at the right time, and this would also reduce the side effects by avoiding over-treatment, bringing a level of precision that traditional methods often lack. Of course, we are not taking the doctor out of the loop, but now we use their expertise as a supervisor and take them to the top of the pyramid. Okay, now, how to bring numerical control into the loop? That's the important point. How do we deal with challenges that we can see? There are two major hurdles over here. First one is a continuous feedback is needed in automatic control systems, which isn't usually practical in clinical settings. We cannot monitor a tumor's response in real time without invasive or costly procedures. This is the main problem, maybe. Continuous feedback is not possible. Second problem, mathematical models are needed in order to run a controller. Mathematical models of the cancer or the biology is needed. And without the model, we cannot use a proper control system or an optimal control system. This is the second big issue. We need a control method that can work around these limitations using data directly rather than relying on the perfect models or constant monitoring. Because in this era, now we are in the data-driven era. Everything is about data. We are using ChatGPTs, LLMs, large language models every day. And it is improving every day. And why not use this technique in biological sciences and control? Okay, now, which method to use then for control purposes? This brings us to the question, which method is the optimal one? We are going to explore two approaches today, mainly the data-driven approach, but before that, I need to discuss another control methodology, which is called model predictive control. And data-enabled predictive control is basically the same with model predictive control, where the model is absent but replaced with the data. Both can address the continuous feedback requirements. Okay, because why? in model predictive control, we have the model of the system. If we have the model of the system, assuming that the model is right, we can do predictions and we can estimate the control signal, the best control signal that we will apply to the patients, or the drug dose that we will apply to the patients in an optimal way for a duration of time. Therefore, instead of taking continuous time feedback from the system or from the patient, what we do, we take the measurements and we predict the next couple of time drug doses and apply to the patient, and then we repeat this procedure. Therefore, continuous feedback problem can be solved by using model predictive control. However, this brings us another problem. What is that? Model predictive control is based on the perfect model. Without a perfect model, we cannot use or we cannot rely on the estimates. And then what we have to do is, mathematical model is not available in general. It is almost always impossible to obtain a precise mathematical model for cancers. It is very complex, very detailed, and every person, every patient has a different model. Then in this situation, what we can do, we can use another technique, which I would call as data-enabled predictive control. Okay, now let's continue with data-driven control then. From model predictive control to data-enabled predictive control. This transition from MPC to DeepC is the key to tackling systems where traditional modeling falls short, like the complex, unpredictable nature of the cancer. Okay, what is model predictive control? Let me tell you a couple of things before that, because not everyone is familiar with that. Okay, it's an advanced control strategy. It's not new and widely used across different industries. It has been used since early 1980s, and the first applications were from chemistry, and probably the first company that it used model predictive control in its systems is Shell, oil and gas company, and they used it in their distillation columns. MPC, in abbreviation, predicts a system's future behavior. It's like a fortune teller or something like that. You can there's a crystal ball maybe inside, right? Predicts the future behavior, but this prediction is based on the mathematical model. And then it optimizes control actions in real time while respecting some constraints. Therefore, what we have over here, we have the controller or the main solver, main solver, which is the optimizer, and we have a model that we use for predictions, and we have a constraint that comes from the physics of the system. And therefore, we can maximize the efficiency and maintain the safety because constraints are under control. They are always considered during the design, and it handles the constraints and adapts dynamically to the changes. It's a very powerful tool. I would like to share some insights from a recent survey carried out by IFAC's Industry Committee. IFAC is the International Federation of Automatic Control, on the impact of the advanced control technologies. And the results clearly show a shift in focus towards smarter more optimized systems. And model predictive control, which currently ranks the fourth in terms of impact, is expected to take the lead in the near future. Meanwhile, PID control, which is proportional integral derivative control, the cornerstone of industrial automation maybe, remains highly relevant, holding the second spot in the future rankings. We also see increasing importance placed on data-driven approach like fault-tolerant detection, process analytics, and estimation techniques. And this growing interest signals a strong move towards intelligent and adaptive control systems that can handle the complexity of modern industry. On the other hand, technologies like game theory, repetitive control are expected to stay niche. They are still in the top 16. In short, the message is very clear. As a researcher and an engineer, our focus should align with the evolving landscape, with model predictive control and intelligent systems leading the way. Okay, let's look at some very fancy applications of model predictive control before we delve into cancer treatment. To give you a sense of MPC's versatility, let's consider self-driving cars first of all. Companies like Tesla and Waymo use model predictive control in their autopilot and driverless systems. It predicts the computer over here. Let me clear all drawings. It predicts the driver system, and there is an autopilot over here. It predicts the car's trajectory and optimizes steering, acceleration, and braking to keep it in the lane, to avoid obstacles, and ensure a smooth ride. It uses lots of sensors like LiDAR systems, cameras all around the car, and MPC processes real-time data to make split-second decisions, showing how it can handle complex and dynamic environments. The second very important application is smart building climate control. For example, this climate control system is taken from Google DeepMind. It uses MPC to optimize the cooling in its data centers. Google has very huge data centers, and they use cooling systems because they have servers, they have thousands of microprocessors inside, and they are like an energy plant. Therefore, huge amount of energy they consume. That's why there is a huge amount of heat inside. They need to cool it, and they use energy efficiently by using MPC, model predictive control. MPC adjusts heating, ventilation, and air condition system to maintain comfort while cutting energy costs. And this demonstrates how MPC can balance multiple objectives like efficiency and performance in real-world settings. Another application is from industry. In industrial setting, companies like Shell, as I told you at the very beginning, the pioneer of this application in real plants, the real processes, and ExxonMobil apply model predictive control to refinery processes, such as crude oil refining. It optimizes operation to maintain stability, to reduce energy, and minimize waste. Of course, by maximizing the profits. By predicting how the chemical reactions will unfold, MPC ensures consistent output. An example of its precision in large-scale systems. They are very large systems and very difficult to control because they are highly nonlinear. There are lots of delays inside, and mathematically modeling is very difficult. Let's talk about some applications from robotics and drones. For example, MPC also shines in robotic fields because of the impressive advancements in the electronics technology. Now we have very high-speed processors, so MPC can use them efficiently to control fast systems like robots. For instance, on the right-hand side, you see the Boston Dynamics robots over here, which is one of them is the quadruped robot over there with 4 legs, like an animal robot. On the right-hand side, the humanoid robot. And it uses MPC for smooth motion, balance, and navigation through complex terrains. Whether a robot is climbing stairs or a drone is avoiding some obstacles for a packet or cargo delivery, we always need some advanced control systems like model predictive control. It's also used in aerospace systems. In aerospace, MPC powers systems like SpaceX Falcon 9 landing system. Probably you have seen this in NASA videos recently. They are using model predictive control to catch the rocket that finish its duty and which returns to Earth. And this backward motion is handled by model predictive control. It's also used in Boeing 787 for the flight control. It predicts and adjusts flight dynamics for precise flight or a stable landing, even under conditions like shifting winds and turbulences. And this shows MPC's capability to handle high stakes, unpredictable scenarios, and those kind of things, so on and so forth. It has been used in smart grids also for real-time energy balancing across Europe. Now you see on the screen as the map of the energy grid in Europe. It's an interconnected system, which means that every country is feeding the other. It optimizes power flow, model predictive control, and integrates renewable energy sources to prevent blackouts and ensure an efficient distribution throughout the network. It predicts the demand and supply fluctuations because it assumes that it has a model, and MPC keeps the grid stable. And the good thing is that it is first developed for small island problems, smart grid problems, like on the right-hand side, where we have lots of houses, factories that use energy, also we have some solar panels which generates energy, also some vehicles that goes into the grid and out to the grid and that leave the grid, and therefore lots of input and outputs we have, and this can be really and easily scaled and used within the inter-country systems like this one in Europe mainland. How does MPC works? Let me explain this a little bit. First of all, it has 3-step process. It's a step process. The first one, it predicts the future behavior using the mathematical model. Okay. For example, on this green box on the at the center of the screen, we have a cost function, and under the cost function, we have the constraints. And one constraint, which is the second line, is x is equal to ax plus bu, which is the mathematical model. Linearized model, but it could be replaced with a nonlinear model. Therefore, the controller, model predictive controller, uses this model to predict the future behavior for a time horizon n. Capital N is the horizon. And then it optimizes control actions to minimize a cost. Here the cost is a quadratic function on the top. It runs from the current time, which is I is equal to 0, up to end of the prediction horizon, which is capital N. This calligraphic Li indicates a cost for stage, therefore it is called stage cost, and calligraphic Ln on the left-hand side stands for the terminal cost. And what it does, it takes this cost function subject to some constraints, which is the mathematical model of the system, also the physical constraints, maybe some states belong to some set X, controls cannot go beyond some limits, physical limits, and subject to these constraints, an optimization is carried out. And a control sequence, an array of control signals are generated, indicated by big U over here. K is the current time. Please keep this in mind. And then this control signal is generated through the prediction horizon. However, only we use the first control signal, which is the UK star. I call it star because it is the optimal one. It is a result of the optimization routine, and this is applied to the process. Process generates an output, probably a state. If it is not a state, we can use an estimator and take this state measurement and repeat this procedure in a loop. Therefore, what we have, as you can see from the top figure over here, we need a plant, we need a prediction model of the plant, we need an optimizer which runs together with the prediction model and the data collected from the system in a loop. There is a residing horizon strategy over here. Okay, let's see how we can handle data. What if we don't have an accurate model? That's the question. That's where the data-driven control comes in to the play. Unlike traditional model predictive control, which relies on good quality model of the system, the data-driven approach designs controllers without prior assumptions about the system structure by just using the input and output data. We have the input that goes to the true plant, which is the process that we control. Also the output, those are measured and handled properly, and we generate a control system using this data. This is a game changer for complex systems like biological ones, where modeling is very difficult or impractical, maybe very expensive to obtain. It's about letting the data speak for itself to guide the control decisions. Now, step by step, we are coming to the point. And let's talk about how we can handle data-driven control. Data-driven control maybe can be considered as shown in the right-hand side of the screen, the evolution of the data-driven control has two parts. Traditionally, we follow two-step process, which is the old one. Identify the model. Then, with that model, we design the controller. However, now we can design controllers directly from the data without using any system identification routine. And therefore, the green line will be the fundamental approach that we are going to follow. Let's see some applications again. On the left-hand side, we have a quadruple tank system, which is a nonlinear process. As you see, for a duration of time, now it is learning at the moment. These are the set points, the dashed red lines for the tanks. We are controlling the levels of the tanks. And it's a very complex nonlinear system. And after the learning phase is finished, which is the indicated on the top as learning phase, deep PC becomes active and it controls the system. On the right-hand side, we have robotic applications. The robot starts from the blue point, which at the origin, 0, 0. It wanders around this point for some time, because at this time interval, the system is learning. The deep sea is not active. And then when it is active, it follows a path and goes to the destination. Two good examples that I would like to share with you. For example, here is a double copter system. We have a air vehicle over here. The target is to bring it to 010 location indicated by a cross sign. And if we run the system, as you see, under the very strong high side winds, which is indicated by the green arrow over here, the robot can successfully reach to the destination. You see the right arrow indicates side wind, and it changes its direction in a sinusoidal fashion. And on the right-hand side, we see the output collected from the system. Okay, now, I don't want to go into details of the system, but I would like to tell you a couple of things. Data-driven model predictive control is based on Jan Willems' fundamental lemma. Jan Willems is a professor from Belgium, and they developed this technique in early 2005 on a systems and control letters paper, which is called A Note on Persistency of Excitation. And after that, especially after 2017, we see a great deal of results derived from this fundamental lemma. This is named after Jan Willems. This lemma applies to linear time invariant systems defined by state space equations. It says that if you have enough input-output data and the input is persistently exciting, which means that it stimulates all the system dynamics, if it is enough rich, you can represent any system trajectory using this data. And this is the foundation of the DPC, which is data-driven approach. A crucial concept is that of persistency of excitation of the inputs. There are input sequences such as U0, U1 up to UT, and these signals should be sufficiently rich in terms of the frequency they capture. The richness is captured by the Hankel matrices. We form this input, we apply to the system, we receive some output y's, starting with y0 up to yt. And this input-output pairs, we only consider the inputs at the moment. We generate a matrix that's, we call it HL over here at the bottom of the screen, and we check the rank. If the rank is full, then we are safe. We can say that our input data is persistently exciting, and then we can use it in data-driven control. And more formally, the lemma states that if the input is persistently exciting of order L plus N is the depth of the system, maybe the number of the states, then any trajectory of length L, such as U bar, Y bar, any trajectory with length L, can be generated by the linear combination of this input-output data that we collected previously. Linear combination means that the linear combination of its columns. Therefore, we look for an alpha that generates this input-output data U bar, Y bar from the collected data on the left, which is indicated by a augmented matrix having components HL for U, HL for Y. Of course, it can be considered as the linear combination of the colors. For example, let's say that on the left-hand side, we have the green. On the middle, we have the blue. On the right-hand side, we have the red. With mixing those colors, we can generate any color over there. It's the same idea, okay? If we have enough rich data on the left-hand side, which is collected from the plant, then we can generate any input trajectory, which is represented by the yellow color on the right-hand side, can be generated by the linear combination of the time series data. Of course, this data might have some problems because not every data is clear. There might be some measurements mistakes, or maybe it would be just too complex and disturbed with the noises. Then what we can do, we can use some other techniques, such as we can look at the most powerful elements in the time series by looking at the singular values of the system. And there is a very good paper over here noted as at the transactions of information theory, how we can judge the data and how we can take out the reliable data and where to cut the data. Indeed, it is indicated in this paper. Maybe you can refer to it if you are planning to use it. And now we collect the data, okay? We collected the data. We apply the lemma to predictive control. We collect input-output data and split it into two Hankel matrices. Each Hankel matrix, on the left-hand side, we have the input Hankel matrices. On the right-hand side, we have the outputs, and we divide it into initial data and the prediction data. Therefore, as you see, we have n plus t ini rows over here. And for each input data, we have the corresponding output data on the right-hand side. The red color indicates that this is the most recent data. The coldest color, which is the bluish one, U0, on the left top corner, it is the most coldest one, which is the oldest one. Therefore, if we are using or if we are updating the system matrices, these Hankel matrices, the red ones are the most recent ones, which we can rely on. And the coldest ones, probably they will have the minimum effect on the system response. And we can consider these two matrices to generate any input-output trajectory. And the problem is how we can predict the future. Of course, we can predict the future with some initial trajectory that is collected from the system with input data. We call it the past data. We generate these columns y data from the trajectory matrix, and then we can use this in the prediction. And here we go. Let's look at the notation over here. As I told you, we collected a very long data and we decomposed it into past data and the future data. Similarly, we repeat the procedure for the output signals as well. Now, what we do, we reorganize these systems. We take the past data, which is the blue one, just under it, we put the YP, which is the corresponding output. And then we put UF, which is the future control signals that we apply to the system, or we think that this would be applied, and then the corresponding outputs. Now, on the left-hand side, we have the old data. We take the linear combination with multiplying with a vector G, and on the right-hand side, on the top, we have the dark U bars, Y bars, which are the collected past and most recent trajectories. And on the under it, we have the red ones, which are the predicted controls that the prediction or the MPC will generate, and the corresponding predicted outputs. Of course, when we solve this problem for G and the red U bar and Y bar, we apply the first control signal of U bar and repeat this procedure. That is the very brief idea. And here is the main results. On the left-hand side, we have the traditional MPC. We have the plant model. We have the cost function. Cost function completely identical, almost identical to the standard MPC. On the right-hand side, we have the data-driven version. As you see, on the left, we have the model, but on the right, we don't have model. We have the data collected from the system and their linear combination. What we do over here, we solve for G, we solve for the U's and Y's, and then apply to the system. This is the idea. I want to skip this nonlinear control approach, but it is the same with the original standard data-driven approach. The only difference is that we update the Hankel matrices during the runtime. Now, let's come to the point. Application of data-driven MPC to the Lewis lung carcinoma. This is highly aggressive lung cancer model. We will use this model to test DeepSea. It's a perfect case study to explore how data-driven control can manage complex tumor dynamics and improve the treatment outcomes. Okay, let me tell you a couple of things about Lewis lung carcinoma. Lewis lung carcinoma is identified in 1951, very old, right? You see, comes from the mouse epithelial cells, and it's widely used in research because it is very similar to the lung cancers, very aggressive lung cancers that can be found in human bodies. Therefore, it would be a good study or experimental pathway for researchers. It has been used widely in cancer drug developments. It's the most important property. It is inducible by injecting tumor cells into mice, which means that you can start this cancer artificially, offering a consistent growth for study. And therefore, what you do over here, you have your mice, you inject the cancer cells, and you wait a couple of times, and then cancer develops in the mouse. Okay? And Lewis lung carcinoma, as I told you, identified in 1950s. It is very aggressive and metastatic and relies on angiogenesis. What does it mean? It means new blood vessel formation, okay, for growth. And this dependency makes it an ideal model for testing anti-angiogenic therapies, like the ones we are going to discuss today. Okay, let's talk about the mathematical model of this tumor. Our model builds on Henfeld's work from 1999, describing the tumor vasculature interactions. We have extended it to include two angiogenic drugs. One of them is angiostatin, indicated by A, capital A. The other one is the endostatin, which is indicated by capital E. It uses 4 differential equations, mainly tracking the tumor volume T. T stands for the tumor volume in millimeter cube, and V stands for the vasculature volume. Drug levels are indicated by A and E, and UA and UE are the drug administration rates, and their units are milligram per kilogram per day. Now, turning to the figure on the right, we see how tumor volume T in blue and vasculature volume V grow over time. Initially, during the starting points, cancer cells are injected to the mice, and there is a minimal growth over here, which is negligible, right? You cannot see it. Maybe if we had used a logarithmic plot over there, you would be able to see the difference, but this is almost negligible at the starting point. But after day 20, both T and V begin to rapidly increase in a sigmoidal pattern like this one, okay? Before stabilizing. And this aligns with the biological intuition. Tumors rely on blood vessels for nutrients, and their growth is closely coupled with vascular support. Interestingly, vasculature volume leads to tumor volume slightly, and this highlights the role of blood supply as a precursor to aggressive tumor expansion. And this follows a logistic graph. We observe in the plot both the tumor volume and the vasculature volume eventually saturate over time, and this behavior reflects the natural limitations built into the model. The tumor cannot grow indefinitely, right? It depends on the vasculature for nutrients, and its growth slows as it approaches to the vascular capacity. And we are going to use this model. As you see, it is highly nonlinear. There are 2 inputs, 3 states, and it would be a good application area for us. Now, let's talk about the simulation setup. For our simulation, we have 2 phases. In the learning phase, from day 0 to day 90, we applied pseudo-random binary sequence of angiostatin and endostatin. Okay, pseudo-random binary means that we are either using 4 milligram per kilogram per day or 16 milligram per kilogram per day, and these are within the safe limits, and the limits are generally 20 milligram. And we use this information for the learning phase. And then during the first 90 days, we take daily volume measurements. Okay, daily tumor volume measurements. After that, after day 90, we pass everything to the deep C, which is the data-enabled predictive control. And learning is finished. We update the control signal every 10 days after that, okay? But I tried 2 weeks time, it worked perfectly. But just to keep it safe, let's say that for every 10 days, we take a measurement, we run the optimization. For the next 10 days, we know what kind of a drug we are going to apply to the patients, okay? And we test the robustness of the system to model uncertainties, also the measurement noises between 1% to 10%. And for simulation purposes, I used MATLAB, ODE 454 solution of the nonlinear systems, and I used YALMIP, an optimization graphical user interface, to represent my nonlinear optimization problem. And so for solving the problem, I used Groby, but any other solver is or can be used easily. Okay, let's come to the simulation results. In case study 1, here you see on the screen, we apply continuous treatments. Okay, the tumor volume drops to 0 over time because during the learning phase, we use pseudo random binary sequence. This is training data. No control is active during the learning time. The system is learning. Of course, you are injecting drug to the patient. At the very beginning, it rises a bit, but later, even during the learning time, the volume of the tumor reduces. After the 19th day, we pass everything to DPC, model predictive control, and as you see, model predictive control, after some transition, settles to a point which is probably 8 or 9 for endostatin, and for angiostatin, it settles to 10.85, which is shown on the top screen. And after that, what happens? The tumor effectively taken under control, and it gets lost, right? It's very active, and the tumor disappears immediately. And this data is collected, or this simulation is carried out for a year. You know, after 1 year, you see about after 5 or 6 months, you see there is almost nothing in the body. Okay. What about the case study 2, which is a bit different? Now, different from the previous scenario, now we pause the treatment from days 250 to 280. And in real life, during cancer treatment, there might be some pauses in therapy, right? Like the one shown over here as with the green area. Sometimes this is necessary. These pauses may be due to severe side effects, for example, organ toxicity, or simply to give a patient time to recover, maybe, right? And clinicians may also use treatment holidays or adaptive therapy strategies to avoid resistance and improve the patient's quality of life. Anyway, in this case study, we clearly see the consequences as displayed over here. Again, we have the learning phase. After learning phase, what happens? The learning phase finish, and on the right-hand side of this dashed line, DPC becomes active. The cancer is under control. But after 250, we pause the treatment, and what happens? The cancer comes back. As you see, it's not good, right? The cancer comes back, and then we start the DPC again, and after some transition period, again, DPC takes the full control, and the cancer gets lost. And let's finish with the case study 3. Case study 3 is about long-term effects. This is the final case study that I explored. Here we introduce 10% uncertainty into the tumor model, okay? Meaning that the system parameters used by DPC are slightly different from the actual dynamics of the tumor. And this mimics real-life situations very well, where biological systems are never perfectly known, right? And where the drug effects or patient responses can vary. What's impressive is that, despite this uncertainty, DPC successfully reduces the tumor to 0 millimeter cube and maintains control for over 700 days. It adapts in real time, relying purely on data rather than exact model, and still manages to find effective control strategy. Now, during the treatments, we have a pause again between days 250 to 280. We again see a sharp tumor regrow. But what happens after DPC resumes in 280, right? It rapidly brings the tumor back down. In the drug input plots, let's focus on this one. We can see system briefly increasing the dose, then gradually stabilizing. This shows how DPC doesn't overreact, but adjusts cautiously and intelligently, even under imperfect knowledge. So, the key takeaway here is twofold. First of all, data-driven control can handle uncertainty remarkably well. And second, continuous therapy is only essential for the first 90 days. After that, every 2 weeks or every 10 days, we can re-update our control strategy. But continuous therapy in overall is essential, as even a short break can cause a major rebound in tumor growth. Let's list some conclusions before I finish. To wrap up, our key findings: DPC successfully suppresses Lewis lung carcinoma using only data with low, safe doses below 20 milligram. It's robust to 1% to 10% noise, but requires continuous treatments. But this is nothing to do with, of course, with the control strategy that we use. It is the property of the cancer, right? Therefore, continuous treatments always needed. And for clinical use, we can use this technique. Looking ahead, okay, we need to optimize data collection for clinical use, explore hybrid approach probably with models, maybe with machine learning tools, and validate these things in trials, right? And what is the fundamental goal? The fundamental goal is personalized adaptive cancer therapy. Personalized means every person is different, every patient is different. We cannot use one-size-fits-all chemotherapy drugs, which are very toxic, but we need to explore these areas. Of course, there are some bottlenecks of this approach. One bottleneck is frequent imaging is needed daily for first 90 days during the training period. After that, every 10 days maybe, right? For control purposes. This is impractical, still impractical clinically due to the cost and the radiation. What's the solution? Of course, we have some solutions, but they are not ready. We can use one promising solution is circulating tumor DNA, okay, ctDNA. It is called circulating tumor DNA as a proxy for tumor volume, okay? What happens probably after some years of time or in research, maybe blood draws could replace imaging with daily at-home tests for training and bi-weekly for you need to go to the hospital just for updating the control strategy. In 5 or 10 days, maybe at-home ctDNA kits and AI predictions could make this feasible, paving the way for clinical trials. And thank you all for your attention. I hope this has shed light on how DPC could transform cancer treatments. If you have any questions or want to discuss this further, please reach out using my email address that you see on the screen. Thank you very much. Now, the chair, maybe you can take control.
Thank you so much, Dr. Ibrahim. Thank you. That was a very interesting presentation there, bringing out innovative ways. I particularly like, the part that says control meets biology. So well done. We really appreciate your time. Engineer Paul, I think we can take one. I know our time is fast spent, so we'll quite speed it up. Well, if anybody has any question, we can take 1 or 2 questions. I think 2 questions maximum. So if you have any questions, you can raise up your hands, and then we'll call you to the question. If not, Dr. Ibrahim has graciously left his email, which we can get in touch with him for any questions or anything further. So is there anyone with any question?